So I want to tell you a little bit about what a coin join is before I get into how to do them. And before I get into what a coin join is, I actually want to tell you what a Bitcoin transaction is. So this is a Bitcoin transaction that I made in Excel. And every Bitcoin transaction has a number of fields, including the version number, which is I always use 2. I always use version 2. That's been the number we've been using for like 10 years or something. But that's the version number. Down at the bottom, there's a field called lock time. And the lock time field is not usually used. It's sort of used for like post-dating a check. If you've ever written a check and then we're like, you can't cash this until March or something, you can do that with lock time. You can create a Bitcoin transaction and say this isn't a valid transaction until block height 1 million or something. It's rarely used though, and it's kind of finicky to use it. But the main things that we use in a coin join are the inputs and the outputs. And you can think of the inputs as the addresses you're sending from, and you can think of the outputs as the addresses you're sending to. It's a little more complicated than that. Like, it also includes the amount, and it includes a ATX ID, and it includes some other stuff. But I like to think of them that way. So in this example, we've got a guy who has an address with 11,000 sats in it and an address with 15,000 sats in it, and he wants to send somebody 20,000 sats. Well, that's a problem because neither of his addresses has enough money. So he's got to combine 2 of them together over there on the left in the input section. He's saying, I'm going to spend from both of these addresses. And then he's got to say, all right, I want to send, whoever I'm sending money to, I want to send him 20,000 sats. And then he creates this thing called change, where after 11,000 plus 15,000 adds up to 26,000. That's more than 20,000, so he's got 6,000 left, right? So he sends that back to himself, and we call that a change output. And then he pays a little bit of it as fee to miners. I'm having him do a 200 sat fee. So that's kind of what a Bitcoin transaction looks like in Excel. Is everyone able to follow along and understand what I'm showing here? Cool. So one of the things you can do with Bitcoin transactions is you can batch them. You can make a big transaction that has many people in it. And exchanges do this a lot. They've got a lot of users. They often batch them together. So here I've got input A, we're going to pretend has 7,000 sats, and we've got a guy here who's sending 2,000 sats to somebody, and then he's giving the remaining 5,000 minus a small fee to somebody else or to himself. And then the next guy's got 28,000, he's giving 21,000 to somebody, plus a little change output for himself. So this is you might do a batching transaction this way, and one nice property about batching transactions is everybody gets a lower fee because they get to share the fee among themselves. Instead of paying 200 sats, each guy's only paying 100 sats, and it's kind of neat. So you get lower fees if you do batch transactions. Cool? You guys following along here? What we're looking at? So when we get into coin joins, what we want to randomize the inputs and the outputs. So here, the numbers are all the same, but I've randomized where they're ordered on here. So we've got, output 5 is right next to output 10, and some of them happen to be equal amounts. Right here, the guys at 5 and 9 happen to both be sending 4,000 sats. But if you're looking at this, you might think, oh, we can randomize stuff, and that'll make it hard for chain analysts to figure out how to follow the funds, because everything's been randomized. But it's usually pretty easy for them. For example, down here at input 7, where it says he's got 90,000 sats, if you're trying to figure out which input that comes from, who can figure that one out? He can. It's really obvious. It has to be the biggest one. So yeah, that's some of this stuff is really easy if you're just doing unequal amounts. The ones that are hard are these two over here. If these are randomized, 5 and 9, you don't really know if that goes with, A or E or maybe even C could have one of those. So that kind of makes it a little difficult to trace. Equal amounts are a good idea. Also, there are no labels. On here, you can kind of tell that A goes with 1 because of the label, and B probably goes with 3 because of the label. But on Bitcoin, we don't actually label them. There are no labels saying these outputs go with these inputs. They're all just unlabeled things. So that makes it a little helpful. But what we want to do is we want to make equal amount outputs. So in this case, I've made all of them 4,000 sats. Everybody's sending 4,000 sats to themselves probably, or to someone. And then you only get the change is able to be easily mapped to whoever sent it. Like you can pretty easily tell that the guy who had 5,000 sats gave somebody, he's got one of these 4,000 sat outputs, and he's also got the change of 900 sats. And that's toxic because you can easily identify that it must belong to this guy, the guy with the smallest amount. But yeah, the equal amounts help with coin joins, and so that's kind of what we want to build, is a transaction that has, it can have a bunch of different inputs of a variety of different sizes, but at least the equal amount outputs will not be traceable to their inputs, because you don't know. There's no labels or anything to tell who put which one in. Everyone good on what a coin join kind of looks like in Excel? So now we're going to try to build that in software, but there's a flow we got to do first. So in the flow here, we usually have a coordination server, and there are 3 rounds of communication between the users of the CoinJoin software and the coordination server who's helping them do this coin join. In the first round, they register inputs. They say, these are the addresses that I'm sending from, and they also register a change output. They say, after the coin join, I would like to receive, the sum of my inputs minus however much the coin join is for, let's say 1,000,000 sats. I would like to receive the sum of my inputs minus 1,000,000 sats into my change address. And the change address is toxic here, but that's fine. It's already toxic in a normal coin join. So, the server can actually see exactly which change output everyone's getting, but that's fine. Everyone on the blockchain can see what change address goes with which inputs. Once the server has the inputs, he gives them something called a blinded signature. And if you've never heard of blinded signatures, let me tell you a little bit about them. Blinded signatures allow somebody to sign a message without seeing its contents and verify later that they really signed it. We use them in coin joins to prove that you sent an input. Like, you registered an input with the coordination server, he gives you a blinded signature, you unblind it and send it back to him, and he can validate that he signed, that he interacted with you, because he can see a signature, but he doesn't know what he's signing. He doesn't know what he signed. So all he knows is you were one of the people who registered an input. And that's important, because in round 2, we're going to register our outputs, and everybody wants to do that part. Everybody would like to receive 1,000,000 sats in a coin join, but they wouldn't necessarily like to contribute 1.5 million sats to a coin join. So the coordination server uses this blinded signature technique to ensure that everybody who gets an output also was part of round 1 and registered an input. But the nice thing about them being blinded is he can't tell who's who. He knows you were someone in round 1, but not who. Once everybody registers their output, he checks the blinded signature to make sure that were part of round 1, and then he prepares a Bitcoin transaction. And it's nice because he's got all of the inputs over here from round 1. He's got some of the outputs from round 1, which are the change addresses, and he's got the rest of them from round 2. So he's got all the inputs, he's got all the outputs. All he needs to do is list them in that Bitcoin transaction, give it a version number, give it a lock time, and now he's got a Bitcoin transaction. But it's not signed. Everybody needs to sign this thing. So that's what he does. He submits this transaction template to everybody, and in round 3, everybody validates that they're getting the right amounts. They're validating that their CoinJoin address is getting, 1,000,000 sats, and their change address is getting, their inputs minus the fee, minus the CoinJoin amount. And everybody checks their own addresses, and then they're like, okay, I'm getting mine, so I will sign this transaction. And if anybody doesn't sign, the transaction doesn't happen. So this is good. It's like you don't have to trust this coordination server, and he broadcasts the transaction, and then you're done. The problem is coordination servers are getting arrested right now. The guy who's running on the right side doesn't exist anymore because Wasabi got arrested, Samurai got arrested, and Wasabi just stopped doing it. You can still use join market, which is great, but I want to show you how we're going to do this without the server. Oh, I had this version that I forgot to use where I would have gone through step by step, but whatever. So here's how we're going to do it without a server, and this is what we're about to build. Everybody is going to publish to a bulletin board, so not a server or not a coordination server, but just a random place where you can put data. Everyone's going to publish their inputs, a change address, and a pub key for use in something called a ring signature. If you haven't heard of a ring signature before, they're used in Liquid and they're used in Monero. And I'm going to tell you a little bit about them. Let's say you've got a group of 3 people, and they all want to do this thing where they sign a message, or at least one of them signs a message, without revealing which one he is, or he or she is. So here they've got a little message called, one of us signed this message, but you can't see who it was. And then there's a signature on it, And you can aggregate all these 3 people's pub keys into something called a ring. And you can take the signature and pass it around on the ring. And you can see, okay, I know that at least one of these people signed this message, but I can't tell which one of them did it. So we use this in lieu of blind signatures because they work in a group setting. Sometimes they're called group signatures. You can tell that, so that's what we're going to use in our serverless version. We're going to publish a pub key in the first step in round 1 to a bulletin board. And then in round 2, we're going to aggregate everybody's public keys, create a ring with them, and when we publish our CoinJoin address to the bulletin board, we are going to publish a ring signature with it that proves we are one of the people who, in round 1, submitted a pub key. And that's great. Then everyone can review that and say, okay, I know that the person who published this output also contributed an input, but I don't know which one he was. And we're doing the same thing the server would have done, but without needing a coordination server. We just need somewhere to post data. Okay, so then after we've done round 2, we do round 3. Everybody checks that the ring signatures are valid, and then everybody prepares and signs the Bitcoin transaction. In order to achieve randomness here, what I'm doing is I'm going to randomize, or I'm not going to randomize, but rather I'm going to alphabetically sort the inputs and outputs. Inputs always have a transaction ID in them. Transaction IDs are a hash, and so they're random numbers. So if the inputs, we order them by the transaction ID, then they get randomized. And then as for the outputs, those are always public keys in Taproot. This thing is built on Taproot. And public keys, when you derive a public key from a private key, you don't know what you're going to get until you do it. So it's random. Thus, if I sort by the ATX IDs on the left side and by the Bitcoin addresses on the right side, I get random sorting without needing to do, and it's deterministic. Like everyone who's in this CoinJoin can prepare the same transaction. So everybody gets the same transaction, they sign it with their Bitcoin key, and they send their message to the bulletin board, and all this happens in round 3. That's the hard round. And then it's broadcast time. Everyone can just pull those signatures off of the bulletin board, validate them, and broadcast the Bitcoin transaction. And if at any step, anyone contributes an invalid Bitcoin address, or an invalid ring signature, or they just don't contribute anything at all, we have a procedure, which I have not yet implemented, for kicking them out. Basically, you require them to publish the private key of their ring signature, and that proves the linkage between what would have been their inputs and what would have been their outputs. And someone won't be able to publish valid data for that because they didn't follow the protocol correctly, and then you kick them out and do it all over again without them. But I haven't implemented that, and that's forthcoming. Right now, it only works if everyone is nice. Okay, so that is what we're going to build, and I don't think we have too much time to build it. We have about 40 minutes, so let's get to it. You guys ready to build this thing? All right, sweet. So I am a weird developer in that I always develop things in the browser. And the reason I do that is because in demos like these, I don't have to waste 20 minutes getting you all to download Rust or something and then figure out, oh, my dependencies don't work because I don't have whatever. Everyone's got a browser, so we're going to develop in the browser, and that makes it so everyone can be on the same page. So open up a new folder, create a new folder in it called, I don't know, you can call it whatever you want. I'm going to call it MSB. So that's the name of the software, MSB. Everybody's going to be an unregistered MSB. And we're going to create an empty file in here called index.html. We're going to open that up in any text editor. I happen to be using Sublime Text Editor because I like it. You can use whatever text editor you want. People at my workshops often use Visual Studio. I've seen people use Notepad. One guy tried to use Microsoft Word. I do not recommend that one. But we're going to copy the code that we see in here, and we're just going to paste it right into our index.html file. And then, you know what we're going to do? We're going to open it up. Open it up in Firefox or Chrome or whatever your browser of choice is. And this is beautiful. We have no errors. The perfect application. I also recommend opening up your browser console. In Firefox, you do that with Control-Shift-I. I believe in other browsers, you may have to go to the little menu, wherever your menu is, and then Tools or More Tools and Web Developer Tools. You should see it somewhere in there. Or you might be able to get away with Control-Shift-I. But you need your browser console open, and then make sure you're in the console tab like I am. So usually multiple tabs. We're going to be looking at stuff in there. All right, everybody with me? We good? No errors? All right, sweet. I did have a guy have an error at this step once. It's like, but whatever. I don't want to say what happened. There are some things that should not be spoken. All right. So the next thing we're going to do is import dependencies. And for our dependencies, let me make this bigger so you can see what they are. Let me tell you about them. One of them is msb.js, which is it's got a bunch of functions in it for interacting with Nostr. That's what we're going to be using as the bulletin board for sending messages to. It's got a bunch of functions for creating inputs and outputs in a Bitcoin transaction. So you can check out the code there if you want to. If you want to see what it is we're working with, it's all right here, msb.js. We've got some stuff for interacting with hex, turning hex into bytes. We've got SHA-256, something for creating inputs, something for creating outputs, and then a bunch of Nostr stuff for interacting with the Nostr as a bulletin board for our stuff. Other dependencies for this include qrcode.js. That's why I was able to show a QR code when we put the address up. Something called ringsig.js, which is a library I created, sort of. I actually just found an existing ring signature library and then packaged it for the browser. But you can check that out if you want to see how ring signatures work. And then we've got TapScript, which is how we create Taproot transactions in the browser. Topher, are you in here somewhere? I think he was going to be. He wrote it. And then we've got Noble SecP256K1, which lets us interact with Bitcoin's elliptic curve and create private keys and public keys and stuff like that. So those are our dependencies. And the next thing we're going to do is we're going to add some style to our page. I know our page is empty, but it might as well be a pretty empty. So just pop this right down here. I'm also going to indent it properly because I like things to be indented properly. Close enough. All right, save that. Let's check out our blank page and see if it looks any better now. Whew, look at that beauty. That is so much better. I love when we apply styles and everything works. I'm really just looking for errors. I don't want to see any red things. It's like, oh, you forgot a semicolon or something. All right, so we're good so far. Next thing we're going to need is jQuery syntax. And I don't like jQuery, but I do like one thing the jQuery people came up with. jQuery was this kind of programming tool, I guess, that was developed back in like the 90s. And they did a bunch of stuff with making it easier to work in the browser. And of all the things they did, it's like 10,000 lines of code. I only like these two. These two pieces of code right here allow you to use a $ to grab elements on your page and then bring them back out. So I always import these two lines from jQuery into all of my projects because I like them, and they make working with the browser much easier for me. The next thing we're going to do is we're going to create our wallet. And you put this one in the body of your document. And if we save this, we should see the semblance of a wallet inside of our browser. So let's check this out. Not that one. No, I don't need him anymore. Refresh this. Look at that. We got a wallet. Now, it doesn't do anything yet. These buttons don't ever do anything yet because we haven't programmed them. And the balance will never finish loading because we have no Bitcoin addresses to even check. But this kind of looks like a wallet, and that's good. We're getting somewhere. Okay, so that's where we're at. Next thing we're going to do is we're going to begin adding some programming to this page. And the first thing we're going to need is a modal. So just put this at the bottom of your body. And a modal is a little pop-up that can show you information. So let me show you how we're going to use it. If I run the command show modal, and then I put some piece of text in there, it'll just pop it up for me. And it also supports HTML. So if I do line breaks or something, then we get line breaks, which is really nice. And you can X out of the modal either by clicking the X or by clicking the background. Nice. That's how you do pop-ups, ladies and gentlemen. At least that's how I do pop-ups. Okay, so we got that all working. The next thing we're going to need is to program our receive button so that it does something. All right, so let's take a look at this code. We're creating a function called receive. When we call the receive function, we use the MSB library, to create a private key and a public key. And then we get a Bitcoin address. From that, we just turn the public key into a Taproot address, because in Taproot we send directly to a public key. So that's good. And then we push the private key to a little object that I call state, so that we store it as a cookie. We actually store our private key as a cookie. Do not use this for actual funds, because any extension you have can read your cookies and steal your private keys, and that is how Ethereum works. All right, don't need you. So if we refresh this and then click receive, we can see a little Bitcoin address pop up in our console. So we're getting somewhere. That's working. So the next thing we need to do is we need to improve that receive button so that it uses our little modal to show us our Bitcoin address with a QR code. I'm going to copy this, and I'm going to paste it. I'm just going to replace this line that says session storage with the new one that also says session storage, but then shows the modal. So if we do that, and then we refresh our page, I don't need this guy or this guy right now, and click receive, check it out. We've got a little modal that has a Bitcoin address in it, and you could send something to that with another testnet Bitcoin address. Pretty neat, right? We're getting somewhere. We got the receive button working. Okay, so receive works. The next thing we need is we need to check if we've received any coins. Because if you send money to this address, or fake money, we're all doing this all in the testnet. If you send money to that address, it won't really show up because we haven't programmed it to even look for it. So that's what we're going to do next. We're going to create a function called getUTXOs. Just put it right down here at the bottom of our script. And getUTXOs will reach out to mutinynet.com, which is my favorite testnet. It will go through our private keys and plug each of our addresses in, derive the addresses from them, and then ask MutinyNet, is there any money in this Bitcoin address? And MutinyNet will give us back an object which we then store in state, so that if we refresh our browser, it'll still be there. The money will still be there. That's what I mean by storing it as a cookie. So yeah, that's what this function does. And then we need to call that function on a loop. So this little loop down here, see what that does. It has a ... at the bottom because we're going to add to it, but ... is invalid, so you can delete the ... So what does this do? Well, if you save right now and refresh, you'll get an error, and I will show you the error. Yeah, uncaught syntax error, missing closing bracket, because we haven't finished this function yet. It's only halfway written. So don't save and refresh like I just did unless you want to see an error. But what this is going to do is, on a loop, it's going to go through all of our UTXOs, all the UTXOs we've stored, and check if they still have money. Like, check if that UTXO is still unspent. Because our wallet, we're going to be occasionally spending our UTXOs, and we don't want them to stay there. We want it to get rid of them if we've spent them. So that's what this first part of the function does. It checks if it should keep a UTXO by seeing if it still exists, and if it does still exist, it keeps it. Otherwise, it gets rid of it. The next part of the function, which is right here, complete the loop. This one, indented properly, goes through all of our private keys and checks if they have, and it passes them into the getUTXOs function, which checks if that private key's public key address has money in it, and then creates a UTXO for us. So by doing that, we add to our state of UTXOs whenever we receive money, and then we check our balance. The last thing it does is, on a loop, it calculates the sum of all the UTXOs you have in your wallet, and then it updates our balance divs, the toxic balance and the regular balance, to say, okay, this is how much money we have. And it does that every 10 seconds. So if we refresh our page now, and we go to click receive, and then we send money to this from MutinyNet. So I'm going to go to faucet.mutinynet.com, give myself 20,000 sats. Then after about 10 seconds, we should see, you have to X out of the pop-up. I have not told it to automatically get rid of the pop-up when the money comes in. But, I also forgot to call the function. So let me do that. I have to call the function. Run the loop is the next slide. So we put this at the bottom of our page. Save and refresh. And now it detected that we have 20,000 sats. So there we go. Nice. Is everybody on this page? Or getting there? Or not seeing too many areas? No, you're all lost? Okay. Okay, there's going to be a live stream, and I hope the audio works now. So you can also follow the live stream later to follow along. Or you can go to the GitHub where it's already completed and just open it up and be like, I'm skipping to the end. So that's another option. All right. So now that we've got the receive button working and we can detect UTXOs we've gotten, I've been told the live stream is working. Great. Awesome. Now that we have the receive button working and we can detect when we've received UTXOs, it's time to make the join button work. And as you might imagine, this is the heart of the wallet, and it's kind of a long it's a long function. 19 sections for this one. But, you know, I think that's to be expected because this is what the wallet is for. It's going to be the thing that takes the longest. Okay, so the first part of this in round one is the part that I am the least satisfied with in my code base. And it is because somehow we need to figure out how many people we're doing our CoinJoin with. We need some sort of signaling mechanism to say, this is the time to start listening for people to register their inputs, and then this is the time to stop. Because if you start listening and people start registering inputs, and they keep registering inputs, and then more people register inputs, when do you stop? When do you come to a close and say, all right, it's been long enough, everyone who's registered so far, we've got to be done. I need to find some way to signal a start time and an end time without having a coordination server. And I've come up with a way that doesn't work, and that's what we're using. But basically, we start looking through the blockchain for a block that if we hash that block and treat its hash as a number, modulo the number 3, we'll eventually, probably the block we give will not be a 0. Will not be a 0 when you take it mod 3. But then we go to the next block back from that one and we check if that one modulo 3 is 0. And if that one's not, we go to the next one back. Eventually, we will find a block where if you treat it as a number and take it modulo 3, you get the number 0. And that is our starting signal. We look at the time when that block was created, and we say that time is when we begin listening for people to register for their inputs. So anyone who registers after that time is good, is in the group. And then when's the stop time? Well, it's the next block that comes out that has, if you modulate it by 3, it becomes a 0. This roughly means that every 3 Bitcoin blocks, we have a round. We have a CoinJoin round. Because we all know the start time, we all know the stop time, and as long as we're all listening during that start and stop time, it's good. This is also, however, I'm not satisfied with this because when I've tried to do this with multiple people, it doesn't work. So somebody who's a better thinker than I am, come up with a better solution for this. Alex has one. What do you got, Alex? Why not just use block height? Yeah, so what you could do is you could say like every block that ends with a 3, a 6, or a 9 is going to be a start, and then the next block that ends with a 3, a 6, or a 9 is going to be a finish. Yeah, you should do that. I should have thought of that. Yeah, one of the reasons why I'm not satisfied with this method is because, well, I actually forget why it doesn't work. But it hasn't worked for me. So someone come up with something, try what he suggested. Maybe that'll be simpler. Anyway, once we've decided on who's going to be in the round, we state what amount we want the CoinJoin to be for. So you can have different amounts in these periods. Somebody can be doing one for 10,000, which is what we're going to do. Another group can be doing it for 1 million. But we publish what amount we're doing it for in our CoinJoin message, and then everybody goes with the group that matches whatever the amount they decided. I recommend using round numbers for this part, but I'm doing 10,000 sats for my CoinJoin rounds. Then we use a get UTXOs function from my MSB library to take our list of UTXOs that we have in our wallet and find some that sums to an amount that's greater than the amount in our CoinJoin, which is like what we were doing in round 1 earlier in the graph in the chart I showed earlier. All right, so that's what that does. And then the next thing is we got to create a change address, because in round 1, there's 3 things we need to send out, if you remember. We need to publish our inputs, a change address, and a pub key for use in a ring signature. So, where was I? I think it was right here. Yeah. So we got our inputs where it says get UTXOs. Those are going to be our inputs. The next thing we need is our change address. So I mark the change address as toxic, and then it goes into our database as a toxic address so that we don't spend that money in another CoinJoin. There's special things you're supposed to do with toxic change that I haven't implemented yet. I just mark them as toxic and then put them in a kind of a separate section of the database. Okay, so that's what we do there. And then we generate our ring signature public key, the public key we're going to use for the ring signature. So now we have all three things that we need in order to complete round one. And so we send them out to our bulletin board, which I'm using Nostr for that. So that's what this section does. We create a little message, and we say, I'm participating in round one of this CoinJoin. We publish the amount that we're doing. We publish a fee rate, and I think I hard-coded in here to use 30 sats per byte as the fee rate because I have PTSD from the ordinals drama, and so that's what I'm using. I think really you should probably check what the fee rate was for the block that for the most recent blocks, and then have some kind of range that you'll accept from other people. But I haven't implemented that. Everyone just uses 30 sats per byte as the fee rate for preparing this transaction, and that works. Okay, so that's what we do there, and then we publish it onto Nostr. We send the event, and we say, okay, now everyone on Nostr knows that we're participating in a CoinJoin referencing the block hash of our current round. Great, we're good. Next, we get everybody's messages, and this completes a round. In computer software design, a round of communication is when you send out a message, and then you get back a message. That's a full round. So we have sent out a message right here to all of our peers, all of the people who are participating in this CoinJoin with us. And then down here, we get all events that match our template. We get all events that look like they're wanting to participate in round one as well. And so that is a complete round. We've sent out a message, received a message, and now we're in round two. If you look back at our little diagram, we are now here at step 2, where we are supposed to publish our output address. We want to say where we should get the 10,000 sats, and we have to include a ring signature. Okay, so that's where we're at, and round 2 begins. All right, paste it. I have not implemented the part where, what I'm supposed to do here is check that everybody's inputs sums to an amount that's greater than the CoinJoin amount. And if they don't, then we're supposed to kick those inputs out and not let them participate. I haven't implemented that, so if you cheat and then you send in 300 sats as an input, people will happily include you in this CoinJoin and you'll get free money. So somebody who's smart, implement kicking people out if they don't contribute a sufficient amount of inputs. I haven't done it yet. Okay, but we create some objects that we're going to use for preparing our ring that we're going to check the signatures against. We prepare an object for putting in all the inputs that are valid, and I just assume they're all valid inputs because I'm not checking. But we need to do that and kick out anyone who's not valid. And then we got change outputs. So we just register the Bitcoin address that everyone's going to use as change in there. We count the number of contributors because we're going to use that later when determining what we're paying as a fee. We have to divide the fee times the size of the transaction and then divide all of that by the number of people participating, and that gives us what we're paying as a fee. And then I have something called mapping, which I use for tracking which fee rates go with which change address so that I know how much to deposit into each change address. I do a little bit of validation down here that they sent in that everyone who's participating in round 1 contributes the same amount as me, and I only include the people in my CoinJoin who want to do a CoinJoin for the same amount. I only include people who are using the same fee rate, but this is the part where it really should be a range of acceptable fee rates because everyone's mempool is different. And I ensure that everybody only contributes a maximum of 2 inputs. You can contribute 1 input or 2 inputs, but no more, because inputs are the expensive part, and if you contribute a whole bunch of inputs, it ruins everything. It makes it so it's really expensive and everyone else has to pay for consolidating your UTXOs. So I just make sure you only have the ability to put in 2. Wasabi used to allow 7 in their coin joins, but that's very generous. I'm only letting you do 2. Well, yeah, but per message, you could only have 7 in each message, and then you could make another message if you wanted to contribute more inputs. Yeah, maybe I'm wrong. I might be wrong about how Wasabi worked there. At some point, I had the impression that there was a 7 involved, but okay. I'm being corrected live, but I appreciate that. Keep me honest, guys. I'm surprised it's taken this long for me to say something wrong. All right, so we get our inputs, and we get everybody's inputs. We add them to the inputs thing, and we check. Oh, actually, I am checking that the inputs sum to the right amount. Oh, that's cool. I did do some validation there. We add their public key to the ring, and then we add their inputs, assuming that they matched up. We add their inputs to the CoinJoin inputs thing, and then we move forward. Next step is to sort the ring. So we sort it lexicographically. That way, everybody has the same ring, because they might receive messages from Nostr in different order. And then I have to have the dummy key, because I found an error, a mistake in the library of the ring sig library that I'm using, where if you happen to be the last person in the ring, it will error. I think it has like an off by 1 bug where it tries to find the next person in the ring to calculate what the next part of the signature should be, and there is no next thing, so it fails. In order to correct for that, I created this dummy key, and we add that as the last member of the ring. And then no one who's actually a member of the ring has this private key, so that it never fails. It never checks against this one. Yeah, I really should use a nothing up my sleeve key, but I didn't do that yet. So this is just one that I generated, and you should not use this one for real. You can use it on testnet, that's fine. Don't use it with real money, because you don't know if I have the private key. Okay, so we do that, and then we get our index after we find out which of the public keys is ours, and we create a signature, a ring signature, that is valid for one of the public keys in there, which happens to be ours. And that's what this function does, make sig. So then we create our CoinJoin address, which is not toxic. We're not marking this address as toxic, because it's actually the kind of address we want in this wallet. And we're going to send our CoinJoin address with our ring signature. And if you'll notice, in our little graph, that is what we're supposed to do in round 2. We publish our CoinJoin address and include a ring signature. So we're following our diagram. So the next phase, down here, is to send that out to Nostr. So we do that, send it out to Nostr. I'm using kind 46,048 rather, for all of these messages. On Nostr, you can make up kinds, and it's wonderful because no one else is using them, since it can be any number between 1 and 65,000. So I just randomly generated this kind, and that's what I'm using for this event. It's one of the things I like about Nostr. No one else sees this unless they're specifically looking for kind 46,000 events. So it's not like going to show up in people's Damus client or something. It's great. So we prepare the event, we send the event, and we have nearly completed round 2. We just need to get everybody's messages. So that's what we're doing here. We get everybody's messages for round 2, and from round 2, and that's it. Then we've done a complete round, and we're now in round 3. Yay! We're most of the way done, 2/3 of the way done with our join function. So the last part, round 3, is the part that is the longest of the rounds. So what are we doing in here? Well, let's paste the code and find out. In round 3, we're supposed to kick out anyone who didn't submit a ring signature or submitted too many outputs to the CoinJoin, or who didn't submit any outputs to the CoinJoin. We're supposed to kick them out by requiring everyone to, if that happens, we require everyone to reveal their ring signature, and whichever people don't reveal the ring signature, we kick out, and whichever people reveal that they did 2 of them, we kick out, and all that stuff. But I'm not kicking anyone out because I didn't implement it, and I'm just assuming everybody's honest. But yeah, you have to kick people out if they're dishonest and aren't following the protocol correctly. And then you restart from step 1 with the remaining people. And it works. It always terminates, at least in theory. I haven't actually implemented it, so there might be a bug. But in theory, it should work. It should always terminate in a successful coin join. But we get all of the outputs. I'm not validating the outputs, so this is another way you can crash this. You can send an invalid Bitcoin address, and then everyone will try to add that to a transaction, and it won't be valid because I'm not checking. But I should do some data validation here. That's for future work. We get all of the outputs, put them in an array, and eventually we're going to sort that lexicographically. I think we do that in the next slide, actually. Let me see. Yeah, we do. We sort that lexicographically so that everything is in alphabetical order. So we get the TX ID and the vout for each input, and we pair them together, and then we sort those alphabetically. And we do the same for the outputs. Except we do it with the Bitcoin address instead. And that gets us a random sorting of the addresses in the output side and of the input side, which is great. Then we prepare our transaction, which is now randomly sorted. And we can't actually use this transaction, though, because the fee, the amount we're putting into the change address is wrong. We haven't deducted the fee for this transaction yet. And then used that to calculate what the amounts for the change should be. So I think every change address right now has like 0 in it. And that's not standard, so you couldn't broadcast that. So to fix that, we do the next step, which is we get the size of our transaction, now that all of the inputs and outputs are in there. And that's what we're doing in this line right here. We multiply the size of the transaction in bytes times our fee rate, which is 30 in this case. And then we divide that by the number of contributors so that everybody pays their fair share for what they're doing. Then we go back through all of our inputs, and for every input that is a change address, that's what we use the mapping object for. For everyone that's a change address, we give it the amount of its inputs minus the amount of the coin join minus the fee that person is paying. And that's their change. And everybody gets change. So we're good. Now we have a valid transaction, and it pays fees, so it can get mined. And at this point, we need to sign it. So, so here what we're doing is we're going through all of the addresses in the input side, checking if they're ours, if they belong to us, and if they do belong to us, then we sign the transaction and exit. I just realized that there's a bug here. Somebody could put one of your inputs as if it was their input, and then you would sign it. But that's only if they know your inputs, which they shouldn't know because they don't see your wallet. So we're good. That's not a bug. We're good. We're still safe. We're still safe. Okay. So then we get our revised transaction with all of the outputs corrected for the change amounts, and then we've signed it now, or we've prepared to sign it. So we create a signatures object, and for every input we create the signature, add it to the signatures object, and then we're going to send this to the bulletin board. Because it's not enough for us to just sign our inputs, we also have to get everybody else's signatures, and everybody else has to get our signature. So we're going to use the bulletin board for this one more time. We're going to submit all of our signature to the bulletin board, and then get everyone else's, and then we'll be happy. So that is the next step. We make a different message for our new ring signature. We still have to prove that we're one of the people involved in this thing. I'm not actually sure you do, though, because if your Bitcoin signature was invalid, then people would just erase it there. Anyway, I'm using a ring signature again, so I make a new message. For the message, I just take the block hash, and I change every other byte to the maximum value, FF, and that is my new message. And I don't think that's insecure. I haven't thought about it much. So then we make a round 3 message. We send in our Bitcoin signatures and our ring signature. And then, this is the last round, we get everybody else's signatures. And we have completed round 3. By the time we get, oh no, we're still just sending. We sent this off to Noster, and then to finish it off, we get everybody else's signatures. And now we are done with round 3. So we've done all 3 of the rounds. The last thing is to broadcast, to put all of the signatures in the right spots and then broadcast the transaction. And then we've done a coin join. Question, Maru? Yeah, I'm doing 10 seconds. You get 10 seconds to do. Once we've reached the next block that is 0 modulo 3, then everyone has 10 seconds for each subsequent round to do the stuff. And that's worked for me so far. So I've not had any trouble with that. If that was troublesome, if some people had shaky connections or were using Tor or something, we would probably need to extend that. But I'm using Noster, which is fast, and it's worked so far. All right, so it's broadcast time. So we get all of the signatures from everybody from Noster, and we check if they're valid and add them to our Bitcoin transaction. You can, of course, crash it here by sending an invalid Bitcoin signature, and then the transaction won't be valid. So if that happens, I need to implement that we kick out anyone who didn't send in a valid transaction, and then we redo it with the honest people who did submit valid signatures, and then we end up getting a coin join anyway. So yeah, it always terminates in a valid coin join, which is a property that I was careful to ensure. Lastly, we get the transaction hex from our transaction, and we show that in the little modal, and we say go broadcast it. You could broadcast it by pasting it into Bitcoin Core. I've been using MutinyNet. They've got a little transaction broadcaster on there, but you've got the transaction. That's the main thing. You could email it directly to a miner as an option. I've done that before. But that's it. There is a send button, but I don't think I want to implement that because I've only got 6 minutes left. But yeah, if you should implement the send button, and I think I need a final closing thing on this transaction, and that should work. We should have a valid software, except you can't send money. But you can coin join, you can receive money, and you can coin join, and that's really good. So that is the CoinJoin wallet. You can finish for homework, you can implement the send function by just copy pasting as I've been doing and make it send money. But are there any questions about coordinator-free coin joins? What's up, Alex? Yes, if you go to mutinynet.com/tx/push, you can paste the transaction hex right there, and it will go through. What's up? What do we miss by having a central coordinator? The coin joins get cheaper, so that's nice because you don't have to pay the coordinator fee. Yeah, what are the downsides of doing it this way? The change is more toxic than it was in the other ones, in Whirlpool. In Whirlpool, at least Whirlpool v1, when you had toxic change, there was a chance that your toxic change would be masked if someone happened to contribute the same amount of inputs as you. And then you would not have toxic change. It would actually be coin joined again because there's an equal amount. This never has that because you send your change in the same message as you send your inputs. So there is a one-to-one mapping between them. And that means our change is super toxic. So a coordinator helps you there. That's the downside of not having a coordinator, is you get super toxic change. Yep. Yeah, eventually it gets too small to put it into a coin join. And then you can donate to the Samurai. Another question? The question is this a coin join or a collaborative spend? Or is Whirlpool something other than Whirlpool is coin join software, and it is collaborative spending software. And all coin joins are collaborative spending transactions, or I call them batch transactions, because there's multiple people and multiple people sending money to other multiple people. So they're all collaborative transactions. But not all collaborative transactions, not all batch transactions, are coin joins, because exchanges do them too, and they're not coin joining. Although they do show up as false positives in my coin join explorer, because they look like coin joins. Yeah, does that answer your question? Great. Any, what's up?
This coin join usually get flagged and you get censored. with this solution, you think it's less possibility to get censored? And one other question is like,
Well, let me answer that question first, and then you can answer do the second one. The question was, does this resolve the issue where if you have coin-joined UTXOs, you get censored? No, it does not. These are just as flaggable. They'll show up in a CoinJoin Explorer, same as any other CoinJoin. Some services won't accept coin-joined coins. So you can imagine, I don't think Bitrefill is an example, but I always use Bitrefill to buy stuff. And someday I can imagine going there and sending them my coin-joined Bitcoin, and them sending it back to me, and being like, return to sender, we don't accept these because it might be money laundered, or something like that. Yeah, so that is an issue with coin joins, is that they leave a footprint on the blockchain that you can tell that they've been coin joined. And governments might put pressure on companies. I think they are already putting pressure on companies to reject them and just send them back to the sender. Or maybe even someday they'll just be like, send them to the Treasury. The US Treasury would like those. But what was your second question?
you did like okay, I'm waiting 3, or for example, I'm taking the vote 3, and you think that all these assumptions you make it. I know this is a beautiful piece of like a beta software. But
Thank you.
like, what do you mean? Do you think this is a way to track kind of your algorithm and also to block from doing this coin join, like a serverless or Nostro or whatever?
A Nostr relay could block these coin joins, and then you just have to find another Nostr relay or not use a Nostr relay. I thought it would be fun. You just need a place where you can post messages and read them. And the Department of Justice has a feedback form. I thought it would be great to use that as our coordination server. And then they would have to sue themselves as money transmitters. So. Thank you all. I hope you have a great rest of the conference. See me afterwards if you have more questions. Thank you.
There you go. Hello, everyone. I'll give a moment to settle the room. Right. Thank you. So, hello, everyone. Thanks for coming. I hope you're not too tired. I guess it's the last presentation for the day and for the conference. And so in this presentation, I want to present some of the work I've been doing on MAT, which is a proposal called Merkelize All the Things. And so in past presentations about this proposal, I focused more on the big theorem, on the fact that you can do very advanced stuff with this proposal. And you've seen Johan presenting progress towards implementing that with implementing the script verification, like verification of arbitrary computation in Bitcoin script. But today I want to focus more on a more simple use case of this approach. And so you've seen a lot of Merkle trees in this conference, but even if the proposal is called Merkelize All the Things, I promise there is only one slide with Merkle trees. And I think I like to start by talking about what is a smart contract and why covenants are so closely related to this idea of doing smart contracts in Bitcoin. So a smart contract is something that looks like this. Like we want to be able to lock some money inside. We want to be able to agree on some state among the parties. State means anything, any content, any variable. If you imagine a program, it could be a chess game, it could be a game of tic-tac-toe. And then you want to have some state transition rules or withdrawal rules, meaning you want to specify how the contract state can be changed by the parties in the contract. So you do some transaction, this transaction modifies the state of the contract. And so this is basically an abstract definition of what a smart contract is. And in Bitcoin, what we have is UTXOs. So UTXOs are very simple objects. You can put some conditions on how you can spend these coins. But as of today, like if you want to do smart contracts with UTXOs, we are a bit limited because you can only set some spending conditions on this UTXO. You do a transaction. So a transaction looks like a transition in a smart contract, so that's promising. But a UTXO cannot specify how the result of this transaction should be. And so if we want to do a transition with a smart contract, what we can do today is, for example, using pre-signed transactions, which you can consider as a form of off-chain covenant, if you prefer. And well, if you watched Andrew Polstra's talk yesterday, you learned how actually there is a way of using Lamport signatures to go around in a clever way on this limitation. But you can easily think that, you can easily understand that, well, if you have some covenants where allow you to program inside the UTXO how the outputs of this transaction should look like, so how the UTXOs that you produce while destroying the ones that you're spending look like, well, that looks like you're able to propagate some state from one UTXO to the other. So that looks promising in terms of doing this kind of computation and this kind of smart contracts. And the proposal that I call Merkelize All the Things is a quite minimalistic approach to Bitcoin smart contract, in the sense that the capability that you need to do this kind of contracts is quite minimal. Like many of these covenant proposals allow you to specify the outputs of the transaction. For example, CTV allows you to specify all the outputs of the transaction at once. And what we want, the core primitive that we want to achieve this capability that I call MAT is that you want to be able to specify the program of the output. So what is the script that the output should have? So in pay to taproot, so in a taproot world, the script is basically the internal key and the tap tree, so the set of all the possible spending conditions. And we want to have some reasonable ways of controlling the amount of these outputs. And then the new thing that I want is that we want to be able to attach some small piece of data to this output. And if I want to also be able, if there is some data attached to the input that I'm running at this time, I want to be able to read this data somehow. And this is mostly the core primitive that we want to achieve. And the only other ingredient we need is that we need to have some opcodes that allow to do something called vector commitments. And a vector commitment means that if you have a set of elements, like what you call an array in a programming language, you want to have a simple way of compressing that into a small piece of data. And we'll see that in a moment, how we can do it. And the claim is that if we have these two ingredients, then we can do arbitrary computation inside smart contracts. And that's interesting because it means that in a certain sense, we can basically implement any possible layer 2 without needing any further changes to layer 1. And the way we do that is by using a tool called fraud proofs, which is what Johan was presenting the other day. And so what is a vector commitment? Like the simplest way of implementing a vector commitment is what we've seen a lot in this conference, which is a Merkle tree. Who is familiar with Merkle trees? Just to have an idea. Okay, most of the people. And but I'll briefly introduce how a Merkle tree is constructed. So in a Merkle tree, what you do is that you have a set of elements. In this case, there are 8 elements. And you hash each of them individually. So hashing an element gives you some form of commitment that is already very short. You can compress anything inside something which is very small. And now, what you do is that you take 2 consecutive elements, you concatenate them, and then you hash the result. And now, from 8 elements, we get 4 elements. We repeat that, we get 2 elements. We repeat that, we get 1 element, and that's what we call the Merkle root. And the reason that's interesting is that now, if you want to prove that the value of a certain element is, for example, the 6th element here is x6, then the other party just needs the Merkle root, which is what we computed before as the root of the tree. And then if you look at the path from the 6th, the leaf number 6 to the root, you only need all the brothers in this path. So the node 5, the node 7, 8, and the node 1, 2, 3, 4, right? Because then, having only these nodes, which are a logarithmic number of nodes compared to the number of elements, you can verify the computation of the Merkle root and check if it matches. So this gives us a tool to compress an arbitrarily large set of elements, an arbitrarily large amount of data in a single hash. And so I've been talking about math as the idea, and like Johan's implementation was based on this opcode called check, contract, verify, and I like to keep them distinct because check, contract, verify is just one possible implementation of the idea. It's a very direct implementation which allows to work with this type of ideas very quickly, but it's not the only way, and I'll show some other examples of how we could get there. And so what does the opcode do? This is for more technical people who want to understand, but already, like, you can think about the framework even if you just understood what is the idea that I presented in the previous slide, which is this one. We want to be able to control program and compute the data. And so the way check, contract, verify works is that you have this bunch of arguments. So you push some data on the stack, you push an index, you push a public key and the top 3, that's the program, and you push some flags. So those are all the arguments of this opcode. And what the opcode does is that you check that the ith input or output of the transaction, or actually the input-output, which index I of the transaction, is a pay-to-taproot script that has the given internal key, public key, and the top 3 as the program, and contains the data embedded. So what does it mean to contain the data? Well, again, that's more an implementation detail, but the way it's done in the opcode is actually that if you know how pay-to-taproot works, pay-to-taproot already commits to some data inside a public key, which is via what is called the taproot tweak. And so since we want to commit to more data inside this same public key, well, we just do the tweak twice. So the first time we tweak the internal key with the data, and the second time we tweak the internal key with the top 3. So in this way, we get a UTXO which is fully compatible with pay-to-taproot. There is no backward incompatibility in the type of scripts that we need. But yeah, it works with quite a simple. We don't require big changes to implement this kind of things. And there are some other special values that you can see below that have some special meaning, like if there are some default values. If you put -1, it usually refers to the current input, and you can use that for the index or for the internal key or for the top tree. Or if the public key is empty, as an optimization, it uses an unspendable public key, which is used in useful in some cases. And if you don't have any data, then it means, well, there is no embedded data, that's fine. And what about the value of the output? We said before that we need some sensible way of also controlling the value of the output. And for many contracts, just piping the value of the input to the output that we are checking is more or less the behavior that we expect. In many cases, we have contracts that are one-on-one, so we have one UTXO that we are destroying, and we are creating a new UTXO, and we just want to preserve the value. But for some contracts, for example, for vaults, it's interesting to do many to one, meaning you have many inputs that they're spending to the same output, and then you want to just sum all these amounts together. And there are some additional flags that are implemented that allow some modified behaviors. One is you can decide, okay, I want to check the program, but I don't want to check the amount. And another one that we'll see a use case later is that you can subtract the amount of this output from the input amount. What does it mean? That if you later have another call to check contra verify with a different output, then you will only check the reduced amount. So you basically pipe some of the amount to some output and then the rest to some different output, and which is niche use case perhaps, but useful for some implementations. And so I mentioned that there are multiple ways of implementing this kind of ideas. And well, the most direct way that I could come up with is with this opcode check contra verify together with opcat. I'm a weird man, so I only use opcat to concatenate things. This is not popular these days. And you can actually implement mat with opcat alone, like Rindal was showing us the other day. And you can actually get also this kind of capabilities if you have more generic introspection on the program of the input or the output, so the SegWit program of the input and the output. Probably in that case, you would also want an opcode like optweak so that you can embed the data inside. And probably there are many other combinations that could achieve these kind of things. And after BitVM and after Andrew's talk yesterday, well, maybe it's possible today, who knows. And so in implementing these things, well, I think it's useful to just play with the tool that we have right now, that we want to discover what we can do with these things. And so my claim is that if you consider, for example, those set of opcodes that are listed there, so check contra verify, opcat, something like CTV or TX hash, and check signal stack, and tweak, plus some other opcodes, like amount introspection and big numbers arithmetic. So a soft fork with all these things is not a difficult soft fork because all those opcodes are relatively simple. And my claim is that, well, I think this can do basically anything. Like, I would be very surprised if someone can come up with an interesting smart contract for Bitcoin that cannot be implemented with this opcode. And of course, also Rusty's project of script restoration would enable math contracts. And so this slide is just to introduce how the framework looks like. So it's a little bit a boring technical slide just to introduce the terms. They will make more sense once we see the code. And so in this framework, what I call a contract is the blueprint of a UTXO. So it's the script and not the embedded data, but how the embedded data looks like. So, so inside the contract, you have what I call parameters, which are all the variables that are already hard-coded in the script. For example, the public keys, or if you have a time lock, it could be the time lock amount, and these kind of things. And a part of the contract is also the definition of what is the data that the contract will contain, so what the UTXO will contain. And then you have a list of clauses, which are the possible spending conditions. And because we have covenants available, clauses also specify not only who's authorized to spend the UTXO, but also what new contract and what new UTXOs are produced by the execution of this UTXO. And so instead, what I call a contract instance is something that is an actual concrete pay-to-taproot UTXO. So in this case, the data needs to be fully decided. This is a real UTXO on chain. It has an address. And so you can actually spend it if you're authorized. And so what I want to show you today is how you can go from having an idea of a smart contract that you represent as a simple finite state machine that changes from one position to another and implement this using this concept, these ideas of smart contracts in a framework that I'll show you later. And so we already saw some presentations presenting this idea of vaults. I'll briefly introduce what is a vault again. So today, when we do a transaction, you can put arbitrary spending conditions in the UTXO, so you can make spending more complicated with multi-signature, with Miniscript, with all these new tools, with Frost or whatever. But those are all measures that you take proactively, meaning before the coins are spent, you make the spending more difficult so that it becomes more secure. And the idea with vaults is that instead of doing this, we want a two-step process. We want reactive security. And so the idea is that, well, you have coins that are in a vault. We want to be able to spend it in a predetermined place. So the coins are still not out of your control. But already in this first transaction, you have to specify what is the final destination of these coins. And so they go to an intermediate state, which I'm calling here unvaulting. And then here, the happy path is that, well, you wait for maybe a day, and after the time lock expires, then the coins can finally go to the destination. And so the destination, so both of these transactions are encumbered by a covenant because on the first transaction, you can only go from vault to unvaulting, and on the second transaction, you can only go from unvaulting to whatever is the destination. And the idea is that, well, at this point, we can add another spending condition to the unvaulting state, or perhaps even to the vault state. And this spending condition can only go to some safe place, which is some address where we secure it in a very secure way. It could be a friend who we trust. It could be a multi-signature where we have keys in deep cold storage. And it's a wallet that we don't expect to use except on emergency. So we can secure it very well because we don't use it every day. And so this is what's the idea with Vault. And so if we think about the framework we have at hand now with Matt, we can build these state machines quite directly. We have these two contracts. So the first contract is the vault, and the second contract is what we call unvaulting. So whatever happens outside, it's outside of our smart contract at this point. And so how do the spending conditions look like? So vault has just one spending condition, which is what we described before, which is we are checking that the first output needs to be the unvaulting script, and we also want that the destination, which is passed as an argument, and so as an argument, it means that it's passed via the witness. So when you spend the transaction, that's when you decide the destination. So this destination needs to be embedded as data inside the unvaulting contract. And we want to preserve the value. That's the logic that we were mentioning before. And so now, how does the unvaulting contract looks like? We have these two spending paths. And so the first spending path is that, well, we want to go to the destination that we claimed before. And so we can check the time lock that we can do with, depending what time lock it is, with check lock time verify or check sequence verify. That's a standard time lock like we use in Miniscript or on Lightning. And the other thing that we want to check is that, well, the destination needs to be exactly what was embedded in this data. And in the demo, I used that. Once we check that so first we want to check that the destination was indeed the embedded data, because as I said before, like the destination is only stored inside the input, so it's not available in script, but you can pass it via the witness, and with check contract verify, you can check the input, so you can check that indeed the destination was the data that was encoded in the script. And then the final check is that well, you can check that the output looks like what the destination was describing. And in the demo, I did that with check template verify, which is convenient for this. You could do that with TX hash, and you could even do that just with check contract verify by checking each of the outputs you want to check directly. And, or actually, well, with check contract verify, you would only have one output instead of allowing multiple outputs. And so this is more or less what it looks like. And the final spending condition that you want is very simple. If for some reason, if someone was trying to steal our money, we don't want this transaction to happen, you have a simple script that checks that the first output exactly matches the expected recovery script. And check contract verify can do that, or CTV can do that. And again, we want to preserve the value. So this is a version of a vault. So this is inspired, of course, by the design that James O'Byrne did for OpVault. And the version in OpVault is more, has a little bit more features than what I presented in the previous slides. And it defines a sort of ideal properties that are quite compelling of what a vault should be. And the demo that I will show actually implements this version of the state machine, so it has all these features. And so what are these features that we want? Well, we want to be able to have reusable vaults, so if you receive multiple UTXOs to the same address, you should be able to use all of them. You should be able to support batching, ideally, so both you should be able to spend multiple inputs from the same vault in the same transaction, but even better if you can batch these together with other transactions, that's great because it also helps with fee management, for example. It's nice if you can allow partial unvaults, which means that in the vault transaction, you can send some money back to the vault immediately, because maybe you have a very large UTXO and you want to only send a small amount. Without this feature, your money will be locked until the time lock expires, which is could be annoying. And you want to be able to choose arbitrary unvault targets, meaning the destination should not be a set of predefined addresses. It should be any address that you decide at the time you want to start a withdrawal. And ideally should have a good fee management. And I put this slide here. This is not existing code. I started using this kind of pseudocode to document the smart contract that I implement. But the reason I wanted to present this is that you can actually think of making this a real programming language that can define fully the kind of contracts that we want to do. And I think it's interesting. It's a very succinct way of presenting these features. And this implements all the features that, even additional features that were not in the slides before. So you have these globals here are basically what I called the parameters before. So they are hard-coded variables that are hard-coded constants that are defined even before you send money to the vault. So those are the keys that you need to unvault, or the keys that you need to send to the recover, or the time block delay. And there are two contracts. This is the vault, and this is the unvaulting. And here there are two spending conditions for the vault, while in the slides I had only one, because here I have an additional spending condition that allows the partial revolt. And this is where this flag of deducting the output amount is used, and I'll show you the code, the actual code later. And so yeah, I don't have interactive demos, so you'll have to trust me if I run things on my computer. It will be the same if you run it on your computer. But yeah, there is a Docker container that has an implementation of check contract verify plus some other opcodes. And in all the demos that I'm presenting today, I'm only using check contract verify, cat, and sometimes CTV. And but yeah, there are use cases for checks from stack that are not yet implemented. And the demos are based on a framework that I've been working on that I call PyMath. In the future, I expect to work perhaps with a language like Rust, but at this time Python, I find it more convenient for prototyping things. And what PyMath allows to do is to give you a framework to semantically defines these objects, defines the contract, and also has objects that allow you, like something that I call the contract manager, that allows you to work with these contract instances to facilitate spending, deriving the addresses, and also tracking what's happening to these contracts. For example, in a multi-party contract, if someone else spends the contract, you need to be able to see the transaction on the blockchain and understand what spending conditions was used so that you understand how the contract state changed, because you will have to react to these things. And the framework automate all these things once you define the contracts. And I have 4 demos implemented so far. So one is the vaults that is similar to the Upvault. I have rock, paper, scissors, because why not? And it's very convenient academic game for playing with these things. And I have an implementation of what I call a RAM, which is just a proof of concept of using Merkle trees to work with large amounts of data inside the contract, just to store and read and write from a memory, let's say. And then I have an implementation of the generic fraud-proof protocol, which is basically the idea of the bisection that allows to do the arbitrary computation. I will not present this today, but since it's popular to show the V-bytes these days, if you implement this with math, the expectation is that for the most complex computations that will do like 4 billion steps, if you implement fraud proofs with math, you will get, in the worst case, so in the non-cooperative case where the entire fraud proof bisection protocol needs to go on chain, the expectation is that the total cost will be less than 10,000 V-bytes, which at today's fees is around $125. So not bad. I have a blog post in Delving Bitcoin that describes all these things. And yeah, demo time. So the last time I ran this demo, the very first command failed. So and I did at least 1 commit this morning. So wish me luck. So yeah, this is a CLI demo of Vault implementation. There is a nice autocomplete, so you can see what are the commands, and you have the Vault address. And so, well, let's go in the history because I have some commands. There is also a nice history which helps with this demo, so I don't have to remember the commands all the time. And so we fund the Vault by sending a UTXO with that size. We fund another one. We do another one. And these demos are all like the transactions happen automatically. So whenever I want to send a transaction, since it's reg test, we can print money and transactions happen. So it's, if you check the last block, you see that there is the last transaction was a 30,000 UTXO, which is the one sending money to the Vault. And now, if we list what the contract manager, which is this object that knows about all the UTXOs, knows, there are these UTXOs that it knows about. They are funded, so they're real UTXOs, and that's what these are. So there are Vault instances with some parameters, and there is no data inside because there is no data inside the Vault contract. And now what can we do to a Vault? Well, we want to start a withdrawal, and let's say we want to spend just the first two UTXOs. So the total amount of these UTXOs, you can see, is 10,000 plus 20,000, but we want to withdraw only 29,000. Right? So what happens if we do this? We wait for the transaction to be confirmed, and that should happen. Okay, it's done. Again, we can go here, and this is the transaction that just happened, and you can see here that there are 2 outputs. One is 29,000 sats, and one is 1,000 sats. And that's because what the transaction that was done was trigger, the close that was executed was the one that I showed before, the trigger and recover, that also has the partial unvaulting. So the first 2 UTXOs are gone, they are spent, don't exist anymore. But now we have 2 new UTXOs. One is in the unvaulting stage, which is the next step of the state machine, and that's worth 29,000 UTXOs, 29,000 sats. And then we have another Vault instance, which is only 1,000 sats, which is basically your change that went back to the Vault. Now, what do we want to do with the Vault? Well, at some point we want to withdraw, right? And so that's item 3. We want to spend this unvaulting UTXO, and we want to withdraw it. So we want that to finally go to the address we said before, and oops, that doesn't work. Why does that not work? Because, well, in our contract we put a time lock, so we cannot yet spend it, right? And so BIP68 is the BAP that defines the time locks that we are using. And so what we can do is we can mine 10 blocks, and those are the blocks that we mined, and now we can try the withdrawal again, and this time the transaction seems to go well, and that's gone to the destination. And again, we can see that in the transaction that is in the last block, there is one output which is 29,000 sats, and is going to this address here, the 10 by 437, and that was the address, hopefully, should be the address that we put in the trigger before. Yep, that's the address. And yeah, that's about it. And now let's start maybe. So now we still have 2 instances of the vault that are still funded. So now we can spend them as well. And here, of course, I'm playing from one command line, but you can imagine that there will be multiple parties involved here, because the people withdrawing and the people trying to steal the money, or people sending to recovery, could be different entities. Could be, you could have a watchtower, for example. And so now we have these 2 items, and we want to send the total amount, all of them, to another address. And that's confirmed. Now again, we have all the UTXOs are spent except the last one, which is the new withdrawal that you started. That's called unvaulting. And this time, someone was trying to steal our money, and we want to we want to recover. And we want to recover item number 5, which is the one we just created. And this doesn't need a time lock, so we can do it at any time. And this is done. And if we look at the transaction that just happened, this is sending to a fixed address, which is what we defined before as the recovery address. And now there is all the UTXOs are spent. So this is about it for the demo of the vault. And I think what's interesting is, what does the code look like to implement something like this? And so in this file, there is the definition of the entire contracts. So we have 2 classes that implement these contracts. One is vault and one is unvaulting. And so the vault takes a bunch of parameters, which are these given here, and those are the parameters that go inside the script. And now in the definition of the clauses, well, first we create the next contract, because we need that inside the code of the script, right? So we create the unvaulting script, the unvaulting contract. No, these are contracts, not contract instances. So those are just how the program works. And now we have 2 clauses here, which are the spending clauses. So I have 2, which is trigger and revolt. So trigger basically wants to spend the whole amount of this UTXO inside the unvaulting stage. And while trigger and revolt also has the partial unvault. So you want to send back some money back to the vault. And if you are spending many instances in the same transaction, which as we did before, normally you will need to use trigger and revolt only once, because you will probably need to just split one of the amounts. Like, there is no need to split multiple UTXOs. So most of them, it's cheaper to not split many of these UTXOs. You would use trigger for most of them. And so this is the entire script, because all you're doing is that, well, you pass the index of the output, you pass what is the destination, and you pass the signature. And the signature is just to prove that you are allowed to do this operation. And so check contract verify checks that indeed you are going to the unvaulting contract. So this is the program. And well, if there is here, let's say we're using 0, which is there is no internal key. And the data and the index are the ones that are passed via the witness tag. So those are arguments that are passed to the close. And so this is all the script. So it's a very small script. And it does basically everything. And together with the script, we also define how the arguments that you need to pass via the witness are defined, including signatures. So this is not really an argument in the contract, but it's just the signature. And this is the actual arguments that we are passing to the close. So this is, we are spending, we are triggering, and we are deciding the destination, and we are deciding that's the output in the transaction. And we also define what are the expected outputs of the transaction, because the framework is not smart enough at this time to figure it out from the script. But we can just say, well, we know that if you do a transaction of this kind, we are going to have a close output that has index out e, which is we pass in the argument, and the contract of this index of this output is unvaulting, and then this defines what is the data contained inside the contract. And trigger and revolt is similar, it's just a bit longer, because before doing the same script that we had before, so the second half is exactly the same, but it also allows to specify an additional output, which is where you're sending the money back, and that has to be a vault. So it's using the same program of the input, so this makes the contract kind of like recursive, because you can go back to your own program. And again, there is no data there, and so this is the deduct logic that we saw before, and then the rest is the same. And then we also have another clause which is like, well, if you want to recover at any time, that we can do, and that's just sending the, this is using check contra verify to send the money to a predetermined public key, which is some taproot address, right? And so that's all the code for the vault contract. And then for the unvaulting contract, we have two clauses, which is withdrawal and recover. So withdrawal is just checking that indeed the money is going to the final destination, but first we have to read this destination. So this is some boilerplate that I simplified with some helper function, but this is basically doing check contra verify on the input to check that the data was indeed what we are passing. And then we check the time lock. And in this case, we don't need signatures because check template verify makes everything not malleable, so should be safe to not have a signature, and so we're using check template verify. And the recovery script is exactly the same as we had before. And so that's all the definitions of the contract, and there is a test suite that actually I wanted to run before and I forgot, which hopefully it works. You can run tests. And I think if you want to implement these kind of things, working with tests rather than with interactive CLIs, it's a bit easier. And the suite also generates a nice report that shows some of the transactions that were produced by the tests. So this is for other things, but the vault transactions are here, and there are some estimates on the size of those transactions, so that's good for comparing. And so if you're implementing these things, how does it look like? So this is examples of tests in the vault. So we have this manager, which is the biggest class in this framework that is able to track all these UTXOs and work with them. And so we define the contracts here at the top of the test. So those are different variants of vaults, basically. And this is just creating the contracts. And if you are looking at this, so this is creating a contract instance. So this is a class that is defined in the framework, which creates a contract instance which is funded with some amount, and this is the contract which is the one we defined before. And so we create whatever arguments that we want to pass. So this is to create the destinations of this transaction. Here we are sending to 3 different addresses. And so this is a contract instance, and we can basically call it a bit like a function. So we pass a signer, so this gives enough knowledge to know how to send this transaction. This passes the arguments, and when you execute this line, this is actually using the manager to send the transaction and track what is produced by this transaction using all the framework we defined. And we know that we will get some instances back because this produces some new contract instances, which is the second contract. And that's a contract instance of a different type, which is the unvaulting stage. And so, this is using trigger and recover. If you do a full flow, which is trigger and withdraw, like it will look like this. You have, again, you do the trigger transactions, and then you produce a spending transaction. Well, those are some of the examples that are a bit more complex. And here is an example where you have to mine some blocks before you can do it. But again, you can ask the manager to wait for the transaction to be spent, and then that will produce the final results. And so that's the thing I wanted to show in terms of code, that like defining the framework, there is really not much more to do other than defining the script. So you do have to understand scripts to start implementing these things, but actually the framework is already smart enough to be able to abstract all the common boilerplate of like encoding, decoding the witnesses, and figuring out these things. That actually the tooling for these things tends to be quite a lot of the work to produce these demos the first time that you do them. And yeah. So yeah, the contracts, don't know if it makes sense to go look too much in the contract, but yeah, basically there is a bunch of classes that are the ones that we are extending earlier that have all these functionalities that are already implemented to get the taproot addresses, to generate the taproot trees and all these things based on the clauses. So that simplifies a lot all the logic of all these contracts. And the manager is the bigger objects in this, which knows how to do all these things. It's connected to the RPC, so it can send transactions, it can receive new block, and make sure it's not production ready. This is good for demos, good for reg tests, but of course you need something more complex for real world implementations. And maybe I'll stop for a moment if there is any question on this so far. No? Yeah.
Scripts again for the unbolting?
Yes. So yeah, this is the unbolting class, and so those are two clauses. So this is withdrawal.
The on-chain, so you looked at last block, like the actual script that had the chain.
Oh, was that the last that we saw? Because maybe we did other. Which screen was it here? Was it here? Yes. Because this one was, this was a withdrawal. So this is the spend from the unbolting state. Which one do you want to see? Which spend do you want to see? Because
I just want to see the script. So where's the check contract verifier?
so, well, you can decode this transaction, I guess.
Yeah. So this looks a lot more efficient than like when I was looking at the outvault.
It's not more efficient, but it's so when I did some comparison, so Upvault, it's optimized for this use case, so of course it's not going to be worse, right? For the exact same features as Upvault wins by a little. Like I didn't find any example where this was more than like 10% heavier, right? But the advantage is that this one is more flexible because you are building the features yourself. So if you want a vault with different features, you can even build the vault with less features because maybe you don't want to have a recovery on the vault phase, or maybe you don't want to have the trigger and revolt, and so you have only one spending condition. So you can find probably some situations where this could even be cheaper than vault because you don't need all the features, for example. Or if you want more complicated constructions, you can do that as well. Or if you want to have multiple, so one thing that is tricky with Upvault is if you want to have multiple spending conditions, both using Upvault, that doesn't work very well because Upvault only removes one of them when you call it. So you will have still a leaf with Upvault, while here, because you are explicitly saying what is the next contract, you can have both leaves still sending to the same contract, so you don't have this problem. So it's more general than Upvault and slightly less inefficient in some cases. It could be more efficient in some other cases. And yeah, that's why I had this example of I made a report at some point so that you can see the transactions. If you go to the vault, there was a gist somewhere where I had the comparison, but I don't remember where it is. Like this is a transaction that has 3 vault inputs, and it's so this is a trigger transaction, and it's like 400 bytes, which is probably very similar to what you will get with Upvault. And okay, so the next demo may be So how much time do we have? It's 10 minutes. So maybe we don't do a lot of other demos. Well, there is. Let's play a quick game of rock paper scissors then. Unless if there are questions and people want to ask something, maybe it's interesting to give. Okay, let's play rock paper scissors. So yeah, we have two terminals here because we have two players, and so we want it is implemented in a way where you can play on both sides. And so, well, we are playing with Alice on the left, and we are playing rock, and we are playing with Bob on the right, and Bob is playing paper. So we expect Bob to win. And so I'll show you execution, then if you have some time, I can show a little bit how the smart contracts work. And so, well, Bob is playing the move. So the first to decide the move is Alice. I'll explain before why this happens even before the smart contract is created. Then Bob plays the move, broadcasts. Bob still doesn't know Alice's move. And, well, Alice knows that Bob wins. Bob is waiting for the adjudication because Alice didn't broadcast the transaction. So now we let Alice broadcast, and now Bob saw the transaction on chain, and this happened. So, well, it works. And for me, the interesting thing is how much code you need to do these kind of things. And if you look at the contract, well, let's not see the contract because we don't have time, but we have two players. So here, it's an example of code where each player only has its own code. So there are two parties. And so they establish a socket because there is some communication here that happens off-chain, where they exchange pub keys, for example, and stuff like that. And then once the instance is funded, Alice already committed to the move inside the contract. And so the contract on chain starts here. So here we're on Rectest, so we found the instance with money directly. And so Alice is just waiting for Bob to play the move. And so Alice has the instance of the contract because she saw it on chain. And just to wait for this to be spent, there is a method in the manager that you can say, okay, I'm waiting for this to be spent. Let me know when that happens. And when it happens, you already get another contract instance, which is the next state of the contract. And on this contract instance, now it's Alice's turn to make the move. Well, Alice will figure out, well, who won. And then the outcome will be exactly the name of the clause. And so you actually spend this again by, you call it a bit like a function, you pass all the arguments, and this actually makes a transaction on chain. And so the Bob's code looks very similar. And yeah, but it plays the other transaction that we didn't see there. And so that's the main thing that I want to convey, that like once this framework starts to have all the pieces, like if you have an idea for a smart contract that you can represent as a state machine, which is mostly any protocol that you can do with smart contracts, going from the state machine to the implementation is pretty straightforward, generally speaking. And so I hope that inspires people to play with these ideas. There are so many things that can be done with smart contracts, and yeah, if anybody wants to play with these things during the hackathon, I have a slide with a bunch of other ideas that are not yet implemented. Some of these might be probably too complex for a hackathon. Some are easier. And yeah, let me know if anybody is interested. I'll be available. Any more questions? Cool. I guess. Is interested in working with this framework or building anything on Math, please feel free to join. There is a QR code there. I'll share the link to the slides.